The universe once existed without a past or future. How did a formless cosmos awaken to the ticking of its own clock and begin to measure its own existence? This is the profound mystery at the heart of time itself. You will uncover how the cosmos learned to track its age, from the first pulse of the Big Bang to the quantum clocks inside atoms. We will explore why time flows in one direction and whether it is a fundamental truth or a cosmic illusion. By the end, you will see reality in a completely new way, understanding your own place within this grand, self-aware universe. How do you think a universe without time would even begin to know itself? That primordial chaos was a realm of pure potential, a state so foreign to our experience it defies easy description. There was no space for objects to exist within, and no time for events to unfold. Particles and energy were not distinct things, but rather ripples in a single unified field, appearing and vanishing in a dance governed by probability alone. This was the universe before it learned to tell a story, a place without sequence or memory. The brilliant insight from thinkers like Stephen Hawking was that time did not simply start ticking like a pre-wound clock. Instead, the arrow of time, the very reason we remember the past and not the future, was born from a single, special condition at the moment of the Big Bang. The universe began in a state of incredibly low entropy. Think of entropy as a measure of disorder, of randomness. A new deck of cards perfectly ordered has low entropy. A shuffled deck has high entropy. Our cosmos started as that pristine, ordered deck. This was the ultimate cosmic seed from which the flow of time would sprout. The second law of thermodynamics states that the total entropy of a closed system always increases, it never decreases. This is the engine of time's arrow. From that initial state of exquisite order, the universe could only move in one direction, toward greater disorder. This is why an ice cube melts in a warm room but never spontaneously forms from the puddle, why you can mix cream into coffee but cannot unmix it. That relentless, one-way slide toward higher entropy is what we experience as the passage of time. It carves the channels of cause and effect into the fabric of reality, creating a past that is fixed and a future that is open. So the flow of time is not an illusion, but neither is it a fundamental entity. It is an emergent property, a story that the universe began to tell itself as it expanded and cooled, moving irreversibly from a state of exquisite order toward a future of ever greater possibility. How did this initial spark of order then forge the first reliable clocks, the cosmic phenomena that would allow the universe to truly begin measuring its own age? That first pulse of existence was not a single moment but a cascade of them, each new state of the universe locking into place the very concept of a before and an after. This was the first cosmic clock, its mechanism driven by the relentless expansion and cooling of everything that is. In those initial fractions of a second, a theory proposed by physicist Alan Guth suggests the universe underwent a breathtaking growth spurt known as inflation. The fabric of spacetime itself stretched faster than the speed of light, smoothing and flattening the cosmos in a process that defined the first great tick of the universal clock. This event imprinted a rhythm onto the newborn cosmos, a sequence of cause and effect that could not be reversed. As the fireball of the Big Bang cooled, it left behind a permanent signature, a faint glow that still permeates all of space. This is the cosmic microwave background radiation. It is the oldest light we can observe, a fossilized echo from a time when the universe was just a hot, dense plasma. For scientists, this radiation is more than just a relic, it is a time capsule. By studying its minute variations, its tiny fluctuations in temperature, we can read the story of the universe's infancy. It tells us how old the cosmos is and reveals the seeds that would one day grow into galaxies. This afterglow is the first tangible evidence of the universe keeping time, a snapshot of a specific moment that has been traveling for over 13 billion years to reach us. With this foundational pulse established, the cosmos had its first crude measure of duration. But a universe that only knows how to expand is like a clock with only an hour hand. For true timekeeping to emerge, the cosmos needed to build something more intricate, something that could mark shorter intervals and create a stable rhythm from the chaos. But to build a clock, the universe first needed a stable fabric, and this is where the story gets deeply strange. As we venture down into the realm of the impossibly small, the very idea of a smooth, continuous flow of time begins to dissolve. At scales trillions of times smaller than an atom, space-time itself is not the serene stage we imagine. Instead, it is a seething, turbulent ocean, a state physicists call quantum foam. In this frenetic domain, the concepts of here and now lose their meaning. Virtual particles, pairs of matter and antimatter, spontaneously burst into existence from nothing, only to annihilate each other and vanish again in a fleeting heartbeat. These are not mere specks of dust, they are fundamental fluctuations in the fabric of reality itself. In this chaotic dance, the neat sequence of cause and effect we rely on becomes blurred. An effect can momentarily precede its cause, and the very tick of a clock becomes a matter of probability, not certainty. The visionary physicist John Wheeler pictured this as a landscape in constant, frothing turmoil, where time might not flow like a river but rather flicker forward in tiny, discrete jumps, like the frames of a cosmic film. This profound uncertainty reveals that time's very origins are not written in stone by rigid laws, but are woven from a tapestry of probabilistic events. It is from this fuzzy, unpredictable foundation that the possibility of measurement first emerged. The chaotic jitter of the quantum world provided the raw static from which the first reliable rhythms could eventually coalesce. So how did this probabilistic frenzy settle into the steady, dependable tick of a cosmic clock that we now take for granted? The answer lies in the universe's relentless drive toward disorder, the very same force that gave time its arrow. A shattered glass never pulls itself back together. The pieces scatter, and that specific, ordered arrangement is lost forever to a new state of higher disorder. This simple, irreversible process is a perfect illustration of entropy in action, the very force that gives time its undeniable direction. Our universe is that shattered glass on a cosmic scale, forever moving from a state of exquisite order toward one of greater chaos. This is the second law of thermodynamics in its essence, a rule stating that the total disorder, or entropy, of a closed system can only increase. It is the engine behind time's one-way arrow, a concept so pivotal that physicist Arthur Eddington gave it a powerful name, the arrow of time. Because of this relentless march toward higher entropy, we form memories of the past but not the future. Stars burn their fuel and cannot unburn it. The entire cosmos is progressing along a one-way street, and this irreversible sequence is what allows the universe to have a history it can record and measure. Entropy acts as a cosmic hourglass, ensuring that events happen in a sequence that can be remembered. It carves the channels of cause and effect into reality, creating a past that is fixed and a future that is open. This unidirectional flow is not just a feature of our daily lives. It is the fundamental reason the cosmos can track its own existence at all. Without this arrow, there would be no before and after, only a timeless jumble of events. So while the quantum world provides the raw, chaotic static of possibility, Entropy provides the narrative structure. It is the author that writes the story of the universe in a single, irreversible direction. And this same author would soon use its most powerful tool, gravity, to carve the first truly reliable clocks from the fabric of space-time itself. Gravity does more than just pull, it literally bends the fabric of time itself. Picture two identical clocks, both perfectly accurate. One rests safely on the Earth's surface, while its twin ventures perilously close to the immense gravity of a black hole. If you could watch them both, you would witness something extraordinary. The clock near the black hole would appear to tick far more slowly than the one on Earth. This is not a mechanical error, it is a fundamental feature of our universe, a phenomenon known as gravitational time dilation. Albert Einstein's theory of general relativity gave us this stunning revelation that mass warps the very space-time around it, and this curvature affects the flow of time. A massive object like a star or a planet creates a kind of dimple in the cosmic fabric, and time flows more slowly at the bottom of that dimple compared to the flat planes far away. This means the universe itself uses gravity as a natural clock, with timekeeping rates that vary from one location to another. We rely on this understanding every single day. The Global Positioning System, or GPS, uses a fleet of satellites orbiting our planet. Those satellites are higher up in Earth's gravitational well, where time actually runs slightly faster than it does for us on the ground. If the satellite's clocks were not constantly corrected for this relativistic effect, the entire system would accumulate errors of several miles within a single day, rendering it useless. This is not a theoretical idea, it is proven operational science. Gravity's influence proves that time is not a universal constant that ticks the same for everyone, everywhere. Instead, it is a relative and personal experience, deeply dependent on your local environment. This is how the cosmos learned to measure its existence with incredible flexibility, running on different clocks in different neighborhoods. And the most profound timekeepers of all were forged when gravity pulled the universe itself into intricate structures, weaving a vast cosmic web that would ultimately dictate the rhythm of everything to come. That faint, cold whisper of radiation that fills every cubic inch of space is the universe's first time stamp. It is the cosmic microwave background, a relic glow from an era when the cosmos was a mere 380,000 years old. Before this pivotal moment, the universe was an opaque, searing fog, a dense plasma of particles and energy where light was constantly trapped, bouncing from one particle to another in a frantic dance. Then, as expansion drove the temperature down, a fundamental shift occurred. Electrons and protons finally combined to form the first stable hydrogen atoms. In an instant, the fog cleared. Light, which had been imprisoned for eons, was suddenly set free to travel across the cosmos. That first burst of liberated light is what we detect today as the CMB, stretched and cooled by billions of years of expansion into the microwave part of the spectrum. It is not just a distant echo, it is a fossilized moment, a baby picture of the entire universe. In 1965, two radio astronomers named Arno Penzias and Robert Wilson stumbled upon this signal while trying to eliminate what they thought was persistent pigeon droppings interfering with their antenna. Their accidental discovery of this omnipresent hiss confirmed the Big Bang theory and earned them a Nobel Prize, but the story of the CMB goes far beyond its mere existence. Scientists like George Smoot and his team discovered that this background is not perfectly uniform. It is imprinted with tiny variations, minute fluctuations in temperature that appear as splotches on a map of the early sky. These splotches are the fingerprints of gravity in its infancy. They represent regions of slightly higher density, the cosmic seeds where gravity had just a little more to work with. Over billions of years, these tiny wrinkles would be amplified by gravity, pulling in more and more matter, eventually growing into the vast cosmic structures we see today, the galaxies and clusters that define the large-scale universe. So the cosmic microwave background is far more than a snapshot. It is the universe's first calendar, marking the precise moment it became transparent and began to keep a coherent history. It provides a fixed point in the past from which all subsequent events could be measured, a foundational beat in the rhythm of cosmic time. With this universal clock now ticking, the stage was set for gravity to sculpt these initial imperfections into the grand, time-keeping structures that would fill the expanding cosmos. From the faint wrinkles in the cosmic afterglow, great cities of stars began to rise. Gravity, the master sculptor, took those subtle variations in density and wove them into a vast, intricate cosmic web. Within this web, galaxies swirled into existence, and with their birth came a new kind of timekeeper. Each galaxy is a colossal clock, its sweeping spiral arms tracing out majestic rotations over hundreds of millions of years. The predictable orbits of stars within these islands of light created a rhythm, a way for the cosmos to measure vast intervals through the pure mechanics of motion. Yet when astronomer Vera Rubin studied these rotations, she found a profound mystery. The stars at the outer edges of galaxies were moving just as fast as those near the center, defying the established laws of gravity. This could only mean one thing: the galaxies were enveloped in a vast, invisible halo of something that did not emit light, a substance we now call dark matter. This hidden mass provides the extra gravitational glue that shapes these galactic clocks, adding a deep, unseen layer to how the universe structures and measures its own existence. The evolution of a galaxy, from a chaotic cloud of gas to a majestic, ordered spiral, marks distinct epochs in cosmic history. These structures show us how breathtaking complexity can emerge from simple initial conditions, creating clocks of such grandeur that they allow the universe to track its age on a scale far finer than its initial, slow expansion. And within these galactic timekeepers, even more precise chronometers were being forged, each one a star burning in the darkness. Every star is a clock burning in the void. A star like our own sun is a master of consistency, fusing hydrogen into helium in its core for billions of years with a steady, unwavering output of light. This stable, middle-aged phase of its life is one of the universe's most reliable long-term timekeepers, but the true measure of cosmic time is revealed not in a star's life, but in its death. For the most massive stars, this end comes in a cataclysmic supernova, an explosion so brilliant it can outshine an entire galaxy. These spectacular deaths are not random events. They are the final, predictable tick of a stellar clock, and they seed the cosmos with the elements necessary for everything that follows. The entire life cycle of a star, from its birth in a collapsing cloud of gas and dust to its final fate, is a process governed by a single, simple factor: its mass. A star's mass dictates its temperature, its color, its luminosity, and most importantly, its lifespan. A colossal blue giant, for instance, lives fast and dies young, burning through its nuclear fuel in just a few million years. A modest red dwarf, however, can shine for trillions of years, far longer than the current age of the universe. This predictable relationship between mass and lifespan means that by simply observing the types of stars in a galaxy, we can accurately gauge its age. This understanding was revolutionized by the work of astrophysicist Cecilia Payne-Gaposchkin. In a stunning discovery, she determined that stars are overwhelmingly composed of hydrogen and helium, overturning the long-held belief that they were similar in composition to the Earth. Her work went further, showing that the chemical fingerprints of stars hold clues to their birth era. The very first stars, known as population 3 stars, were pure hydrogen and helium. When they died in supernova, they forged the first heavier elements like carbon and oxygen and scattered them across space. The next generation of stars, population 2, formed from this enriched material containing a tiny trace of those metals. Our own Sun is a population 1 star, rich with the heavy elements cast off from countless stellar generations that came before. So by analyzing the chemical composition of a star, we can read its lineage and place it within a specific chapter of cosmic history. This process of stellar nucleosynthesis, the creation of new elements inside stars, provides a timeline written in starlight itself. It shows us how the universe uses the birth, life, and death of its stars to track the passage of epochs. From these immense stellar furnaces, we now look to the smallest building blocks of reality, where timekeeping becomes a matter of quantum perfection. Deep within every atom, a tiny universe keeps perfect time. While stars mark the eons and galaxies trace majestic rotations, the most precise clocks in existence are built upon the quantum vibrations of a single element, cesium. An atomic clock does not rely on gears or pendulums, but on the fundamental rhythm of matter itself. It counts the oscillations of a cesium atom as its electrons jump between energy levels, a process so regular and unchanging that it forms the very definition of a second. Since 1967, the international standard has been based on this exquisite quantum dance. 1 second is officially defined as the time it takes for a cesium atom to oscillate exactly 9,192,631,770 times. This is not an arbitrary number, it is a direct measurement of a constant in nature, a heartbeat of the universe that is the same everywhere. The genius of physicists like Norman Ramsey was to create a method, now known as the Ramsey method, to probe these atoms without disturbing their delicate quantum state. By isolating cesium atoms in a vacuum and bathing them in precisely tuned microwaves, they could measure this natural frequency with breathtaking accuracy. The best modern atomic clocks are so precise they would not gain or lose a single second in over 100 million years. This incredible precision reveals a profound truth. The universe did not just create time as a vague flow, it built the potential for its own measurement directly into the fabric of matter. At the quantum scale, the cosmos discovered a perfect metronome, a rhythm born from the immutable laws that govern electrons and photons. This is how fundamental particles enable the cosmos to know itself with such exquisite detail. From the chaotic birth of the universe to the predictable ticking of a cesium atom, we see a clear progression toward stability and order. And this same drive toward stable rhythms did not stop at the quantum realm. It found another, more ancient expression in the very chemistry of life, where biological systems began to track time on a scale far more personal to us. Life itself became a timekeeper, deep within nearly every living organism, from the simplest bacteria to the human body. A silent, persistent rhythm beats in tune with the planet's spin. These are our circadian rhythms, internal biological clocks that orchestrate our sleep, our wakefulness, and even our metabolism over a roughly 24-hour cycle. This is not a mere reaction to the rising sun, but a profound anticipation of it. Life has internalized the cosmic clock of Earth's rotation, evolving biochemical processes that align with the predictable rhythm of day and night. The pioneering work of biologist Franz Halberg, who coined the term chronobiology, revealed how these internal timers are fundamental to survival. They allow a flower to open its petals just before dawn, or a nocturnal animal to stir at twilight, optimizing their functions to match the environment. This is the universe measuring its own existence through the lived experience of life. The cosmic principles that govern the spin of galaxies and the oscillation of atoms have been woven into our very biology. Our own sense of time, the grogginess of jet lag when we cross time zones, is the direct result of this deep, evolutionary programming. It demonstrates a breathtaking feedback loop where the grand physical ticking of the cosmos inspires biological rhythms that, in turn, allow creatures to navigate their world. This intimate connection between the celestial and the cellular forces us to ask a much deeper question. If time is not just a physical parameter but a lived experience, what is its true nature? Is the flow of time a fundamental reality? Or is it, in the end, the most convincing illusion the universe has ever created? Yet, even as our atomic clocks tick with near-perfect precision, we are confronted by a question that has haunted thinkers for millennia. Is the river of time a fundamental current of reality, or is it merely a story our minds tell us to make sense of the world? The philosopher Immanuel Kant proposed a radical idea that time is not something we discover out in the universe, but rather a fundamental framework of our own perception. He saw it as a necessary lens through which we experience reality, a stage that our minds build so that events can unfold in a coherent sequence. In this view, the universe without a conscious observer might not possess a past or future at all, but simply exist as a static block of all events, a concept physicists call the block universe. This stands in stark contrast to the cyclical understanding of time found in many Eastern traditions. Hindu cosmology, for instance, speaks of immense cycles of creation and dissolution, where the universe is born, exists, and is reabsorbed in a rhythm spanning billions of years. This is not a linear march from a beginning to an end, but an eternal, repeating process like the inhale and exhale of a cosmic being. These cultural lenses profoundly shape how we interpret time's arrow. Is it a one-way street leading to a final destination, or a spiral where every end contains the seed of a new beginning? The physicist searching for objective time in the curvature of space-time and the philosopher probing the structures of human understanding are asking the same essential question from different angles. Does the universe learn to measure its existence through emergent processes like entropy and atomic vibrations, or is time an inherent, pre-existing property that we are merely uncovering? This inquiry pushes beyond physics and into the realm of conscious experience, for it is within our own awareness that the flow of time feels most vividly real. The present moment seems uniquely immediate, a sharp point separating the settled past from the unknown future. But is this now a fundamental feature of the cosmos, or is it the brilliant, convincing construct of a mind trying to navigate a vast and complex reality? Your own consciousness is the most intimate clock you will ever know. It weaves a chaotic stream of sensory data into a smooth, unbroken narrative, creating the powerful illusion of a present moment that flows from past to future. Neuroscientist David Eagleman explores this intricate process, revealing how your brain is not a passive recorder of time but an active constructor. It collects signals from your eyes, ears, and skin, but these signals arrive at different speeds. Your brain performs a remarkable feat of editing, stitching them together into a single, coherent story and presenting it to you as the now. This is why your perception of time is so fluid. When you are fully absorbed in a captivating task, hours can feel like minutes. In a moment of sudden danger, however, your brain goes into overdrive, recording memories with such density that a few seconds can feel stretched into an eternity. This is time dilation under stress, a clear sign that your internal clock is governed by attention and emotion. Even the strange feeling of déjà vu, that eerie sense of having lived a moment before, might be a minor glitch in this delicate neurological timing mechanism. These subjective experiences demonstrate that our measurement of time is not purely external. It is a complex negotiation between the objective ticks of an atomic clock and the deeply personal, interpretive machinery of the mind. This suggests a profound possibility that the universe's ability to measure its own existence may ultimately rely on conscious observers to interpret its signals. The cosmic story requires a reader. The objective flow of entropy and the subjective flow of conscious experience are two sides of the same coin, blending together to create the rich tapestry of a temporal world. Long before we understood quantum vibrations or cosmic expansion, humanity felt this deep need to mark the passage of time, leading to the very first calendars and clocks born from observing the heavens. Massive stones still stand in silent alignment with the rising sun. Ancient cultures around the world, from the builders of Stonehenge on the English plains to the Mayan astronomers in Central America, looked to the heavens and saw a clock. They constructed monuments that functioned as colossal calendars, their stones and pyramids precisely oriented to capture the solstice sun or mark the equinox. These were not just buildings, they were humanity's first great attempts to impose order on the flow of time, to mirror the universe's own innate rhythms here on Earth. By tracking the sun's shifting path and the moon's recurring phases, they learned to measure the year and predict the turning of the seasons. This was a profound partnership with the cosmos, an effort to read the sky as a vast celestial instruction manual for when to plant, when to harvest, and when to conduct sacred ceremonies. Anthropologists and archaeoastronomers like Anthony Aveni have dedicated their lives to decoding these ancient systems. They reveal that for these early cultures, time was not an abstract concept. It was a living, cyclical force deeply woven into their mythology, their agriculture, and their very understanding of existence. The Mayans, for instance, developed an incredibly complex calendar system that interwove a 260-day sacred cycle with a 365-day solar year, creating a grand calendar round that took 52 years to complete. Their ability to predict celestial events like eclipses with remarkable accuracy demonstrates a sophisticated awareness of cosmic patterns that echoed the universe's own developmental journey. These early timekeepers were not merely observing, they were participating in the cosmos's story, using the predictable motions of the sun and moon to anchor their societies in the great, unfolding narrative of time. This deep historical need to measure, to predict, and to find our place within the cycles of the cosmos set the stage for every timekeeping revolution that would follow, driving us toward ever greater precision in our quest to capture time itself. A sundial measures a day, but it cannot measure an hour with any real precision. For millennia, humanity's relationship with time was tied directly to the sun's arc and the slow creep of a shadow. This all changed within the monasteries of medieval Europe, where the need to mark the hours for prayer spurred a technological revolution. The first mechanical clocks emerged, not with faces and hands, but with bells that would ring out across a town, marking the canonical hours with a new, authoritative voice. These early machines were crude, their timing governed by the slow, erratic release of a falling weight. Yet they represented a profound shift. Time was no longer just a force of nature observed in the sky. It was becoming a commodity, something that could be manufactured, contained, and shared by an entire community. The intricate gears and escapements of these clocks externalized time's measurement, pulling it from the heavens and bringing it down to Earth. This was the universe's self-awareness filtering into human society, allowing for coordination on a scale previously unimaginable. The true breakthrough came in the 17th century with the Dutch scientist Christian Huygens. By harnessing the regular, predictable swing of a pendulum, Huygens created a clock that reduced error from minutes per day to mere seconds. This was not an incremental improvement, it was a quantum leap in accuracy. The pendulum clock transformed timekeeping from a public announcement into a personal possession, a precise tool that could synchronize everything from scientific experiments to the schedules of emerging industries. This technological leap reflected a deeper cosmic trend, the universe's own journey toward creating ever more stable and reliable rhythms. From the quantum oscillation of a cesium atom to the steady tick of a grandfather clock, the drive for precise measurement is a recurring theme in reality's story. And just as humanity believed it had finally tamed time into a perfect, universal beat, a patent clerk in Switzerland would reveal that time was far more fluid and mysterious than any clock could ever show. Albert Einstein wove time and space into a single, dynamic fabric. His theories of relativity revealed that the three dimensions of space and the one dimension of time are not separate stages but deeply intertwined, a unified entity we now call spacetime. Picture this fabric as a vast, flexible sheet. A massive object like our Sun creates a deep dimple in this sheet, and the planets orbit by following the curved geometry of this warp, much like a marble rolling around a funnel. This is not a force pulling at a distance, but an object responding to the shape of the stage itself. Einstein showed that this curvature does not just guide the path of matter, it directly influences the flow of time. This leads to one of the most fascinating consequences, the twin paradox. Imagine one twin stays on Earth while the other travels on a spaceship moving at nearly the speed of light. Upon the traveling twin's return, she would be significantly younger than her Earth-bound sibling. Her high-speed journey did not just feel shorter, time itself literally slowed down for her relative to everyone else. This is not a mechanical error or a trick of perception. It is a fundamental property of our universe. Time is not a universal constant that ticks the same for everyone. Its rate is relative, dependent entirely on your speed and your local gravitational environment. This unified view was a monumental leap in the cosmos's ability to track itself. Time became a dimension that could be measured, warped, and woven into the very structure of reality, allowing for a far more intricate and interconnected form of self-awareness. But if the Sun can gently bend the fabric of time, then what happens in a place where space-time is curved so severely that it forms a bottomless pit? This is the domain of the most extreme timekeepers in the universe, the enigmatic black holes. At the edge of a black hole, time itself grinds to a halt. This boundary is known as the event horizon, a point of no return where the gravitational pull becomes so intense that not even light can escape. According to Einstein's general relativity, if you could watch an object fall toward this abyss, you would witness a strange and chilling sight. The object would appear to slow down, its image reddening and dimming until it seems frozen forever, etched onto the horizon like a ghostly photograph. For the outside universe, time for that object has effectively stopped. Yet, for the individual making the fall, the experience is entirely different. Their own clock ticks forward normally as they cross the threshold, unaware of the eternal tableau they have left behind for observers. This paradox reveals a profound split in the nature of time, where a single moment can be both an endless freeze frame and a fleeting personal passage. The work of Stephen Hawking added a breathtaking layer to this mystery. He discovered that black holes are not entirely black. Through the bizarre rules of quantum mechanics, pairs of virtual particles can pop into existence right at the event horizon. Sometimes one particle falls in while the other escapes, stealing a tiny amount of the black hole's energy in the process. This slow, faint leakage is now known as Hawking radiation. It means that even these ultimate prisons of gravity and time are not permanent. Over trillions upon trillions of years, a black hole can evaporate, fading away and returning its information to the cosmos in a final, gentle whisper. Black holes represent the most extreme environment for measuring time, places where our cosmic clocks are stretched to their absolute limit and our definitions are challenged to the breaking point. They force us to confront the most fundamental questions about time's own story. If time can be brought to a standstill, then did it also have a definitive beginning, and could it ever meet a final end? Cosmic time is the universe's own master clock, a bold attempt to define a single, shared present for all of existence. This theoretical framework sidesteps the personal, relative time of Einstein's universe to ask a grander question. Can we find a timeline that belongs to the cosmos as a whole, a story written from its own perspective? Cosmologists construct this idea by averaging the universe's contents over immense scales, smoothing out the galaxies and voids into a uniform cosmic fluid. This simplification allows them to rewind the expansion, tracing a single, coherent history all the way back to the Big Bang. The astonishing uniformity of the cosmic microwave background provides powerful evidence for this view. That cold, even glow tells us that when the universe was young, it was remarkably similar in all directions, establishing a foundational beat against which all subsequent events can be measured. This shared rhythm implies a preferred cosmic time, a universal clock that ticks in sync with the expansion itself. Yet this elegant picture is not without its complications. The violent frenzy of quantum foam at the smallest scales and the incomprehensible speed of inflation in the earliest moments introduce profound uncertainty. They remind us that the universe's smooth, average history emerges from a foundation of probabilistic chaos, where measurement is never perfectly straightforward. The concept of cosmic time ultimately reveals a deeply self-referential universe, one that uses its own large-scale properties to define the very timeline of its evolution. To fully grasp this self-awareness, we must venture to the frontier of physics, where the nature of time itself may be rewritten by a theory of quantum gravity. At the most fundamental level, reality may be stitched together from a fabric of tiny, woven loops. This is the radical proposal of loop quantum gravity, a theory that reimagines the very essence of spacetime. Pioneered by physicists like Carlo Rovelli, it suggests that space and time are not smooth and continuous, but are instead composed of a network of discrete, one-dimensional loops, trillions of times smaller than an atom. In this view, the familiar flow of time is not a primary ingredient of the cosmos, but an emergent property that arises from the quantum interactions between these fundamental threads. The universe, in a sense, learns to tell time through the changing connections in this cosmic tapestry. Each tick of this ultimate clock would occur at the Planck scale, the smallest possible unit of time, a duration so brief it makes a nanosecond seem an eternity. This discrete network challenges our deepest intuitions, proposing that time does not flow like a river, but rather clicks forward in the tiniest of digital steps, one quantum of spacetime at a time. How does this change our understanding of measurement? If time is granular, then the smooth sweep of a clock's second hand is a grand illusion, an average of countless microscopic transitions in the underlying structure of reality. The universe measures its existence not against a background of continuous time, but through the evolving relationships within its own quantum fabric. This perspective offers a profound answer to the puzzle of the Big Bang's beginning, suggesting that the collapse of spacetime could reverse into a prior universe's expansion, a cosmic bounce rather than a singular creation from nothing. This stands in stark contrast to another great quest for a unified theory, one that portrays the fundamental ingredients of reality not as loops but as vibrating strings. String theory suggests that time itself may be a melody vibrating through hidden dimensions. In this radical framework, the fundamental building blocks of reality are not particles but unimaginably tiny, vibrating loops of energy. Each distinct vibration pattern gives rise to a different particle, from photons to quarks, and the dimension in which these strings vibrate could include the very fabric of time we perceive. The familiar, linear flow of our daily lives might be just one single note in a vast, multidimensional symphony. This vision, championed by brilliant minds like Edward Witten, proposes that what we call time is not a fundamental stage but an emergent property arising from a more complex, higher dimensional geometry. The implications are staggering. In such a cosmos, other universes could exist on vast, vibrating membranes or brains floating in a higher dimensional space. Rain cosmology speculates that our universe's entire timeline, from the Big Bang onward, might have been set in motion by a cataclysmic collision with another such brain. This contact could have imprinted our cosmos with its initial conditions, including the low entropy state that gave time its arrow. Imagine our universe as a single page in an infinite book, where each page has its own rules for time, its own direction for cause and effect. In some of these sibling universes, time might have multiple arrows flowing in several directions at once, or it might be a closed loop with no beginning and no end. These are not mere philosophical speculations but serious attempts to solve the deepest puzzles of quantum gravity. They push the origins of time beyond our observable horizon, suggesting our cosmos is just one participant in a far broader temporal landscape. If our universe is part of a multiverse, each with its own unique clock, then the ultimate end of time must also be reconsidered. Does time have a final destination, or does it simply transform into something beyond our current understanding? The universe's final story may be one of deepening silence. In a future so distant it defies comprehension, the cosmos could reach a state known as the heat death, where the great thermodynamic engine that gave time its arrow finally runs down. All the stars will have long since burned out, their fuel exhausted. The last black holes, after eons of slowly leaking Hawking radiation, will have evaporated into a faint mist of particles. Across this vast, expanding darkness, the temperature will approach a uniform, frigid absolute zero. In this equilibrium, there are no hot spots and no cold spots, no differences in energy that can be harnessed to perform work. It is a universe without gradients and therefore without the capacity for change. When every process that can happen has happened and no new events can occur, does the concept of time still hold any meaning? Without a sequence of before and after, the universe loses its ability to measure its own existence. The physicist Freeman Dyson pondered whether any form of consciousness could endure in such an era, perhaps by operating on unimaginably slow timescales, harnessing the last vanishing whispers of energy. Yet even this seems a temporary reprieve against the relentless tide of entropy. This ultimate fate brings the cosmic story of time full circle, from a formless beginning to a changeless end. It suggests that the universe's self-awareness, its capacity to tick and talk, is a temporary and precious phase in its long history. Just as the cosmos learned to measure itself, it may one day forget. This profound contemplation of time's end has always been mirrored by humanity's own cultural attempts to capture its essence, reflecting our deep need to find meaning within the relentless flow. Ancient myths did not describe a universe that simply began, but one that breathes. In the vast cycles of Hindu cosmology, time is a great, rhythmic exhalation and inhalation. The universe is created, endures for an almost unimaginable span, and is then dissolved, only to be born again in an endless cosmic dance. The goddess Kali embodies this relentless rhythm, her imagery capturing both creation and destruction as inseparable parts of a single, timeless process. For the Aboriginal peoples of Australia, the dream time is not a past event but a continuing reality, a foundational era when ancestral beings sang the world into existence, weaving time and landscape into one enduring story. These narratives reveal a profound understanding that time is not a blank slate but a dimension rich with meaning and purpose. The anthropologist Claude Lévi-Strauss spent his life studying how myths function. He found that across cultures, from the Americas to the Pacific, stories about time serve a vital purpose. They are not primitive science, but sophisticated tools that structure a chaotic world. By personifying the sun as a chariot rider or the seasons as battling brothers, myths translate the impersonal forces of the cosmos into a language of human drama. They transform the frightening randomness of thunderstorms or the mystery of death into a coherent narrative, one where time has a role and a reason. This act of storytelling is itself a form of measurement. It marks significant cycles, it defines eras, and it connects human lives to the turning of the stars. The Greek Titan Kronos was not just a symbol of time, he was time, a primal force that devoured his own children, illustrating the inevitable consumption of all things by the future. These cultural lenses show us that humanity's earliest attempts to measure existence were never just about counting days. They were about finding our place within a vast, living cosmos. The universe was learning to track its own age through entropy and atomic vibrations, and we, in our own way, were trying to do the same through story and symbol. This deep, ancestral need to find pattern and meaning in the flow of events laid the essential groundwork for a new kind of inquiry, one that would eventually seek to strip away the myth to reveal the underlying mechanism. The most profound equations of quantum gravity contain no variable for time at all. The Wheeler-DeWitt equation, a cornerstone of attempts to unify general relativity with quantum mechanics, paints a startling picture of a static universe. It describes the entire cosmos in a single, frozen moment, a state physicists call the timeless wave function of the universe. Within this framework, the relentless flow we experience is nowhere to be found. How can this be? Physicist Julian Barber offers a compelling interpretation. He suggests that what we perceive as the passage of time is not a fundamental river, but an illusion generated by the changing relationships between quantum particles. Each unique configuration of the universe, which Barber calls a now, is a single point in a vast landscape of possibilities. Our conscious journey from one now to the next creates the powerful, persistent feeling of a moving present. It is like watching a film where the illusion of motion comes from a rapid sequence of still frames. In this view, the universe does not evolve in time, it simply is, and our experience of time emerges from comparing one static snapshot to another. This challenges the very core of measurement, for if time is not fundamental, then what are our clocks actually measuring? They are not tracking a universal flow, but rather counting correlations between one quantum event and another. This idea is being put to the test in laboratories around the world. Scientists are using entangled particles, those spooky twins of the quantum world that remain mysteriously linked across any distance. By studying how their connection behaves, researchers are probing whether time itself has a quantum nature. Could two events be entangled in time, not just in space, creating a new layer of temporal connection we have yet to understand? Alongside this, some theorists propose that time might be a fundamental field, much like the Higgs field that permeates all of reality. In this model, the ticking of a clock would be a direct interaction with this temporal field, a measurable force as real as gravity or electromagnetism. These competing visions show that the universe's process of learning to measure itself is far from over. each new experiment, each refined equation, brings us closer to understanding whether time is the ultimate stage or merely the most convincing actor in the cosmic play. This relentless refinement of our models has not remained in the realm of abstract theory. It has quietly revolutionized the very devices we use to navigate our daily lives, embedding the most exotic principles of physics into the technology we hold in our hands. Your smartphone knows exactly where you are because it is in constant conversation with the cosmos. The global positioning system is a technological marvel, but its true genius lies in its reliance on time, accurate to within a few billionths of a second. Each satellite in that constellation carries an atomic clock, and your phone triangulates its position not by distance, but by the precise time it takes for those satellite signals to arrive. Without correcting for the effects of both special and general relativity, where time on the satellites runs slightly faster than on Earth, the entire system would fail in a matter of minutes, throwing your location off by several miles. This is not an isolated case. The entire digital world is synchronized by a silent, universal heartbeat. Every financial transaction, every piece of data exchanged across the internet, is stamped with a timestamp derived from atomic time. The Network Time Protocol, or NTP, constantly nudges computer clocks into alignment, creating a coherent global network that prevents digital chaos. This intricate web is humanity's ultimate echo of the universe's own journey toward self-measurement. We have built a societal nervous system that operates on a timescale far finer than human perception, from the nanosecond precision of high frequency trading to the coordinated pulses that keep our communications flowing. In mastering these rhythms, we have not conquered time, but have instead learned to dance to its fundamental frequency, mirroring the cosmos's innate drive for order and synchronization. This practical mastery inevitably turns our gaze forward to the role time will play as we reach beyond our own world. A journey to the nearest star system would rewrite the very definition of a lifetime. Proxima Centauri, our closest stellar neighbor, sits over 4 light-years away, a distance so vast that a spacecraft traveling at a fraction of light speed would take decades to reach it. Yet for the crew on board, time would not pass as it does for mission control on Earth. According to Einstein's special relativity, the faster you move through space, the slower your clock ticks through time. Astronauts on such a voyage would return to a world where their friends and family had aged far more than they had, a real-world consequence of time dilation that transforms interstellar travel into a one-way trip through time itself. This is not science fiction, but a fundamental principle that space agencies must confront. To navigate the void, they use the universe's own most reliable timekeepers, pulsars. These rapidly spinning neutron stars emit beams of radiation that sweep across space with the precision of a cosmic lighthouse, their rhythmic pulses stable enough to rival our best atomic clocks. By triangulating a spacecraft's position using these distant, pulsing beacons, we can create a galactic positioning system, a testament to using the cosmos's own rhythms to find our way. This introduces the concept of proper time, the personal, subjective time measured by a clock carried on a specific journey. For an interstellar traveler, their proper time is the only timeline that matters, a personal odyssey measured in their own heartbeats, completely detached from the calendar years ticking away back on Earth. This practical application of time's fluid nature shows how our grasp of its origins is the key that unlocks the stars. Yet as we prepare to send human consciousness on these immense journeys, we must also ask how the mind itself would cope, trapped for years within the confines of a ship where the only clock is the relentless, silent progress toward an invisible goal. A boring lecture can make 5 minutes feel like an hour, while an exhilarating adventure makes hours vanish in an instant. This chasm between the clock on the wall and the clock in your mind is the domain of subjective time, a psychological layer to our cosmic story. The pioneering psychologist William James explored this curious fluidity, noting how a period rich with new experiences feels long in the moment but short in memory. Your brain is not a passive clockwork mechanism. It is an active interpreter, and its primary currency is attention. When you are engrossed in a captivating task, your brain enters a state of flow. Neurochemicals like dopamine flood your system, and your internal metronome seems to speed up, causing you to underestimate the passage of objective time. Conversely, during moments of boredom or anxiety, your brain is starved of stimulating input. It actively scans the environment, checking and rechecking the clock, and this heightened awareness of time's passage makes every second feel painfully drawn out. This reveals that our perception of duration is deeply tied to how much information we process. A routine commute where your mind is on autopilot leaves little memory trace, making the trip seem to have passed in a flash. But a commute where you witness a startling event becomes densely packed with memorable data, stretching your subjective experience of those same few minutes. This internal clock can be profoundly affected by neurological conditions. For individuals with attention deficit/hyperactivity disorder, or ADHD, the brain's management of attention and executive function works differently. This can lead to a phenomenon known as time blindness, where estimating the length of a task or feeling the approach of a future deadline becomes incredibly challenging. The brain's timing circuits, which rely on a delicate dance of neurotransmitters, simply do not fire in the same rhythmic pattern. This isn't a character flaw, but a clear window into the biological machinery of time perception. It shows that the universe's grand project of self-measurement finds a unique and deeply personal expression within each conscious mind. We are not merely reading the cosmic clock, we are each building our own version of it from moment to moment, based on our feelings, our focus, and our very neurobiology. This profound role of the observer forces us to confront a new question. If our experience of time is so deeply personal and malleable, what responsibilities does this power of perception bring? The radioactive waste from a single nuclear power plant remains hazardous for hundreds of thousands of years. This staggering timescale forces a profound ethical question upon our present generation. Our everyday choices, from energy consumption to environmental policy, create ripples that will travel far into the future, touching the lives of people we will never meet. This is the challenge of deep time, the moral duty to consider the eons that will follow us. The philosopher Hans Jonas framed this as an ethics of responsibility, a principle that urges us to act so that the consequences of our actions are compatible with the permanence of genuine human life on Earth. It is a call to expand our temporal horizons, to align our brief human lifespans with the immense scales of cosmic history. The universe learned to measure its existence across billions of years, and we are now challenged to do the same in our decision-making. Adopting this cosmic viewpoint transforms our role from temporary occupants to stewards of an ongoing story. It asks us to weigh our immediate desires against the well-being of generations yet unborn, to ensure the planet we pass on is not a diminished inheritance. This shift in perspective is how we honor the vast, unfolding narrative of time itself, accepting our small but crucial part in its continuity. And just as philosophy gives us a framework for this responsibility, art provides the emotional language to feel the weight of deep time, translating its abstract immensity into something we can see, touch, and deeply comprehend. Salvador Dali's melting clocks drape over barren landscapes like tired slugs, their forms surrendering to an invisible, syrupy flow. This famous painting, The Persistence of Memory, does not show us what time is, but how it feels, a visual poem about the plasticity of our inner experience. Dolly captures time not as a series of ticks, but as a single, languid dream where past, present, and future dissolve into one another. Literature, too, has forged its own clocks. The French writer Marcel Proust spent thousands of pages exploring how a single scent, like the taste of a Madeleine cake dipped in tea, could unleash a torrent of vivid childhood memories, collapsing decades into an instant. For Proust, the true measurement of a life was not in hours lived, but in the depth and resonance of moments remembered. These artists reject the rigid tick of the atomic clock, offering instead a map of time's emotional terrain. They remind us that the universe's self-measurement includes the rich, subjective tapestry of human consciousness. Storytelling has always been a laboratory for time. Ancient epics like the Mahabharata weave together nested tales and prophecies, where the past directly speaks to the future. Modern science fiction films play with time loops and alternate histories, creating narratives where cause and effect are tangled knots rather than straight lines. These stories are more than entertainment. They are thought experiments that mirror the quantum uncertainties at the heart of reality. They ask what might happen if we could step outside the river of time and observe its flow from the bank. In doing so, art becomes a vital partner to science, a tool the universe uses to explore its own nature through the lens of human creativity. It adds the essential dimensions of memory, regret, hope, and wonder to the cold, hard facts of entropy and relativity. This creative questioning inevitably leads us to the most tantalizing and controversial frontier of all: the possibility that time's arrow might not be fixed in one direction forever. A wormhole is not just a tunnel through space, but a potential bridge across the ages. These hypothetical shortcuts in the fabric of space-time, permitted by Einstein's equations, could connect two distant moments as easily as they connect two distant locations. If one end of a wormhole were accelerated to near light speed and then brought back, time dilation would ensure that end had aged less than the stationary end. You would then have a doorway leading directly into the past. This theoretical construct, known as a closed time-like curve, would allow an object to return to its own starting point in both space and time, creating a loop in its personal history. The brilliant work of physicists like Kip Thorne has explored whether the universe's laws might actually permit such a journey. The challenge is not just building the tunnel, but keeping it stable. To prevent the wormhole from instantly collapsing, you would need a form of matter with negative energy density, something exotic that pushes space-time apart rather than pulling it together. While we have glimpses of such exotic effects in laboratory experiments, the amounts needed for a traversable wormhole remain far beyond our reach. This is not just an engineering problem, it is a deep question about the universe's own consistency. Could the cosmos allow for a timeline with loops in it without the entire structure of cause and effect unraveling? This question leads directly to the most famous objection to time travel, a puzzle that has haunted storytellers and scientists alike. What would happen if you traveled back and prevented your own grandparents from ever meeting? This grandfather paradox presents a stark, logical inconsistency. If you were never born, you could never have traveled back to change the past in the first place. So how could the event ever occur? Physics offers several compelling ways out of this conundrum. One possibility is that the universe operates with a kind of cosmic censorship. Any attempt to create a paradox would be physically prevented. Perhaps your gun would jam, or you would simply be unable to bring yourself to pull the trigger. The timeline would protect itself through a series of increasingly unlikely coincidences, ensuring that events play out as they always were meant to. Another, more radical solution comes from the many worlds interpretation of quantum mechanics. In this view, your journey to the past would not actually be a journey into your own past, but a branching off into a new, parallel universe nearly identical to your own. In that new timeline, your actions would create a new future, one that you could never return to because it is not your own. This resolves the paradox by making every possible past a reality in some branch of the multiverse. These theoretical frameworks show that the universe's capacity for self-measurement might be far more complex than a simple, linear arrow. It could include non-linear paths and even loops, a web of potential histories that the cosmos could, in theory, navigate. This thrilling possibility pushes at the very edges of our understanding, forcing us to ask what time's ultimate nature must be for such wonders to even be conceivable. The universe does not just create matter and energy, it generates and processes information with every event. This profound connection between time and data was first illuminated by the pioneering work of Claude Shannon, whose information theory gave us a new way to measure uncertainty and order. In this framework, entropy is not merely a measure of physical disorder, but a direct measure of missing information. A state of high entropy is one where we lack the specific details to describe a system's exact configuration. Think of a shattered vase. The moment it breaks, the precise arrangement of every fragment represents a massive increase in information, a chaotic story that is incredibly difficult to reconstruct. Over time, as those pieces are scattered and lost, that information effectively vanishes from our view. This is the one-way flow of information, mirroring the one-way flow of time itself. The universe seems to learn the direction of time by processing information through irreversible events, where data is either created or permanently lost. This creates a deep puzzle when we confront the most destructive objects in existence. A black hole, with its immense gravity, consumes stars, planets, and light, swallowing an unimaginable amount of information. For decades, physicists were tormented by a question. When a black hole eventually evaporates through Hawking radiation, what happens to all that information? Does it simply vanish from reality, violating a fundamental tenet of quantum mechanics that information must be conserved? This black hole information paradox strikes at the very heart of our understanding of time and reality. If information can be truly destroyed, then the universe's ability to keep a consistent history, to have a past that can be measured, is an illusion. The resolution to this paradox may be one of the most beautiful ideas in modern physics, the holographic principle. It proposes that all the information describing a volume of space, including everything that happens within it, is actually encoded on its two-dimensional boundary, like a cosmic fingerprint. A black hole's entire interior could be described by information painted on its event horizon. In this view, the three-dimensional world of our experience, complete with the flow of time, emerges from the complex processing of information on a distant, two-dimensional surface. Time itself may not be a fundamental property of the deep cosmos, but a projected illusion arising from these informational relationships. This transforms our concept of measurement entirely. A clock is not just tracking an independent river of time, it is reading out the results of a cosmic computation. The universe begins to resemble a vast dynamic computer, where the laws of physics are the software and the unfolding present is the output of an ongoing calculation. The cosmos functions by constantly updating its state, processing the information of the previous moment to generate the next. This computational view ties the very origins of time to a process of logical operations, suggesting that the universe learned to measure its existence by learning to compute it. Time is the universe's most successful invention. From the first irreversible slide into disorder after the Big Bang to the steady pulse of a cesium atom, we have traced a journey of increasing precision. The initial low entropy state set the stage, providing the one-way arrow that made a sequence of events possible. Then, gravity stepped in, sculpting the faint wrinkles of the cosmic microwave background into galaxies and stars, creating vast clocks that tick with the rhythms of orbital mechanics. At the quantum scale, the universe embedded even more reliable metronomes, the immutable oscillations within atoms that define a second with breathtaking accuracy. This progression reveals a cosmos not merely existing within time, but actively building it layer by layer through the complex interplay of its fundamental laws. Relativity showed us that time is a flexible dimension, woven into the fabric of space-time and warped by mass and motion. Quantum mechanics revealed the probabilistic, grainy foundation from which this smooth flow emerges. Cosmology provided the grand narrative, the story of cosmic time written in the expansion of space and the afterglow of creation. Together, they form a unified picture where time is not a pre-existing stage but a dynamic process, an emergent property that the universe cultivates as it grows in complexity. This is how the cosmos learned to measure its own existence, not with a single clock, but through a symphony of structured interactions, from the gravitational dance of galaxies to the biochemical rhythms of life. The profound implication is that self-awareness, the ability to track and record a history, is not an accident but a fundamental feature of a complex universe. We are not just observers of this process, we are participants. Our own consciousness, with its fluid perception of the present, is the latest refinement in this billion-year-old project of cosmic timekeeping. We are the universe's way of not just measuring time, but of giving it meaning. Our journey through the origins of time reveals that our reality is not a stage where a pre-existing clock simply ticks. Time is an active, evolving feature of the cosmos, cultivated through billions of years of increasing complexity. From the chaotic quantum foam at the smallest scales to the majestic rotations of entire galaxies, the universe has tirelessly built intricate clocks to track its own journey. This progression from a featureless beginning to a cosmos rich with rhythm reflects a deep, self-referential intelligence, a universe that is not merely expanding but is actively learning to observe and measure its own existence. Every moment you experience, from the steady beat of your own heart to your perception of a fleeting second, is a part of this grand, ongoing narrative. You are intrinsically connected to this cosmic process of measurement, a living participant in the universe's quest to understand itself. We would love to hear your own thoughts on time's enduring mysteries in the comments below. If you enjoyed this journey into the unknown, please subscribe for more explorations of reality's greatest enigmas. Thank you for joining us in unraveling the story of time itself.